He is a part of the team models of computing complexity and combinatorics at Laboratoire of de l'informatique et du parallélisme. I think that since 2019, he is a research director at INRIA in the Laboratoire de l'informatique du parallélisme hosted by École Normale Supérieure de Lyon. And I have to mention that Dr. Fewzi Omar has obtained the CNRS bronze medal in 2019. His research focuses mainly in quantum information, applied probability, and theoretical computer science. Again, I will thank Dr. Fewzi for this opportunity to talk in our webinar. And please, Doctor, you can start, and you have approximately 50 minutes. Thank you for your attention.
So yeah, thanks a lot, Rafiq. So maybe I'll share my screen. Do this. So I hope, yeah, you can see it.
Yes,
well.
It's okay.
So we'll try to make it full screen, but okay, I should have done it in the opposite way. Can you
like
see
this?
it?
Yes, like this, it's okay.
You can see it now.
Yes.
And does it move or not?
No.
No, okay, yeah, so I should do it in the other way. I will stop sharing now. Now it should be better.
Yes, better, yes.
Okay, excellent. Okay, so yeah, so thanks a lot for this invitation. So yes, so I'll be talking about a specific topic in quantum information theory. So in particular, I'll focus on one specific task, which is certified randomness generation using the laws of quantum theory. And so as I was saying, so I expect that the audience is rather broad. So my talk will be rather more of an overview. I'll try to enter a bit more in some of the details, but there will be no proofs. Okay, so let's start. So first, I'll start by just a very general overview of what quantum information processing is about. So this is a big area of at the intersection of computer science, physics, and mathematics. And the objective there is to exploit the laws of quantum theory in order to do information processing in a more efficient way. Okay, so a bit more specifically, in today's computers, at the basic level or the basic building block of them is information is encoded in a two-level system. Okay, so this could have physically multiple realizations, like for example, it could be that there's current or there's no current in a wire. It could be the direction of magnetization, for example, as in hard disks. But really, we tend to not think about the physical way in which we store information, but we abstractly think of this building block as a bit. Okay, so our classical computers, as we call it, is composed of a bunch of bits. Okay, and we represent it mathematically by just bit b, which takes two values, which we represent by 0 or 1. Okay. So now I'm going to be talking about quantum computers, okay, which are computers which use the laws of quantum mechanics. And so this building block, okay, which was represented by a bit, whose state was represented by a bit, now will become what we call a qubit, okay, for quantum computers. So a quantum bit. And now, instead of encoding information in what we call a classical system, which has two distinct states, like either current, no current. Now it will be what we call a two-level quantum system. Okay, so this could be, so similarly here, there is multiple possible physical realizations. So this could be, for example, the polarization of a photon, could be the spin of an electron, which are known to satisfy the laws of quantum mechanics. Okay, so and so we know from the laws of quantum mechanics that the way to represent mathematically the state of such a qubit is, instead of just having two possible values, okay, so like 0 or 1 in the case of a bit, now the right way of representing it is by a unit vector, by a complex unit vector, okay, which you usually denote in this way, like with this ket psi. Okay, so for example, we could have the states 0 or 1, which is like the classical case, but we could also have arbitrary superpositions. Okay, so it could be, I could have a vector in between 0 and 1, so which is the uniform superposition of 0 and 1. Okay, so properly normalized so that it has a unit norm, okay, unit L2 norm. Okay, so you can also have complex numbers, so that's why I put the complex number I here. Okay, so a qubit has more possible states. Okay, so it could be in superposition of the different states here that I call 0 and 1. Okay, so I won't talk too much and even at all about the formalism of quantum theory in this talk. I'll stay at a higher level, but yeah, just the basic idea is this. Okay, is that we're allowed to have superpositions. Okay, so the first question you can ask is why care about such quantum computers, about such computers which use the laws of quantum theory? And so I'll try to mention to you some applications of such quantum devices. Okay, so as you of course all know, we currently don't have quantum computers, but these would be applications of quantum devices if we had them. Okay, so let me start by mentioning these applications we know of such quantum computing devices. Okay, so historically, probably the first idea of using the laws of quantum theory for computation came by the physicist. I mean, was derived by the physicist, very well-known physicist Feynman in the 80s. And so his motivation there was to use a quantum computing devices in order to simulate complex quantum systems, right? So you imagine you have a very complex molecule, for example, which really its properties depend very much on the laws of quantum mechanics. And so if you want to understand its physical and chemical properties, then this is difficult to simulate on a classical computer. However, if we had a computer that itself uses the laws of quantum mechanics, you could determine such properties in a much faster way. Okay, and so this is what I put under the umbrella of quantum simulation here, which is to use quantum computing devices in order to determine quantum properties of physical materials. Okay, so these could be materials, could be molecules. And so, yeah, okay, so this is the first application, and maybe even this will be the most important applications of quantum computers when we see them. Okay, because, so here I mentioned a specific example of interest here. So this is a specific molecule which governs the given process, which is used a lot of nitrogen fixation. So this is used a lot for making fertilizers. And if we could understand this phenomenon better, then we would save a lot of energy. Okay, so yeah, so this is an example of a specific problem, but there are really many physics questions which we could advance significantly if we had a quantum computer. Okay, and so for such problems, the algorithms we have on quantum computers achieve an exponential speed up relative to the best classical algorithms we have for these problems. Okay, so this is the first class of examples I wanted to mention. And so this is probably not very surprising, right? So if you use a quantum machine, it's normal that it will be able to simulate quantum processes more efficiently. Okay, but one really big breakthrough in the area of quantum computation came in with the algorithm of Shor in 1993. who considered quantum algorithms for a problem which a priori has absolutely nothing to do with quantum mechanics, right? So it's a very natural and very old problem. It's the problem of factorization, right? So here you're given an integer, which I denoted by n here. So think of it as a very large integer. And okay, so to find its prime factor. So imagine n is equal to p times q. I have two prime factors. I want to find both p and q. Okay, and so the amazing thing here is that Shor was able to find a quantum algorithm which runs in time, which is polynomial in the number of digits of n. Okay, so the number of digits of n is log n. Okay, and so the running time is polynomial in this log n. Okay. Whereas even despite lots of work in this area, in designing classical algorithms, the best current algorithm we have is exponential in the number of digits. Okay, so it's slightly, I mean, it's an exponential to some power which is less than 1, but nonetheless, this is exponential. Okay, so for this problem, we have an exponential speed up using quantum algorithms over the best known classical algorithms. Okay, so there are also other classes, like, for example, problems in linear algebra, like, for example, the very fundamental problem of solving a linear system or of computing the eigenvalues of a given matrix, etc. So there's lots of work in this direction, especially in the last few years. And for such problems, depending on the exact problem and the exact formulation, so we usually have either a polynomial speed up or sometimes in some very specific models, we do have an exponential speed up. Okay, and so these are just some examples. There are also other examples of some problems for which we do have a speed up by using the laws of quantum mechanics. Okay, so I should mention here maybe some word of warning a bit, is that sometimes in the in the press you would hear that quantum computers would be able to make everything faster. This is not very accurate to say that. So it's not like a quantum computer is not a black box that you press on a button and everything will become faster. It's really, I mean, the way I think about it is it's a completely new computing devices, and so you really have to design new algorithms there. So there are problems for which quantum computers can help. There are other problems for which quantum computers will probably not help. Okay, so and we have to really rethink algorithmically the different problems and see for which problems we can find a speed up. Okay, but as I presented here, so there are already several computational problems for which we do have such a speed up. Okay, so this was in terms of computation and obtaining a speed up in terms of computation, but a quantum computer or quantum devices more generally can have other applications. So there are other things you can do with quantum devices, in particular quantum communication. So one famous application is so-called quantum key distribution. Okay, so it's a protocol where you have two parties that communicate quantum bits between themselves. And so at the end of this communication, they're able to establish a secret key. Okay. And and this is information theoretically secure as opposed to the best we can do classically, which is computational security. Okay, so so I won't discuss more here. This was just to give you an overview of the potential applications of quantum devices. Okay, so given all of these applications, why do we not have quantum computers at the moment, and what is the difficulty in building such large quantum devices? The difficulty is that quantum systems are usually very noisy. Okay, so and it's very difficult to prepare quantum states which are very stable and at the same time controlled. Okay, so the difficulty is exactly this tension between controlling a quantum system and having it be stable. Okay, so if you want to compute with these devices, you have to be able to control it. So in the sense that you have to be able to say, that at this moment, I should apply a given gate between qubit number 10 and qubit number 15. But at the same time, you don't want it to interact too much with the environment, because this will make it unstable. Okay, so this is really the difficulty of having this tension between controllability and stability. And this, of course, increases as you have larger devices. Okay, but we're seeing significant progress in recent years. In particular, as you might have heard, there are massive investments towards quantum technologies at different levels, and we have seen multiple progress in recent years. So in particular, so for example, all the big tech companies like Google, IBM, Amazon, or Microsoft, they all have a very large quantum team, okay, who are trying to build the quantum computers. Okay, we have multiple startups on an international level. Here I mentioned just some examples at the level of France. There are huge funding programs. Again, this is internationally, but at the European level, you might have heard of this quantum flagship. And so in terms of the progress we have seen recently, let me mention this, maybe this one of the most famous progresses in the last few years is this progress by the Google team. Okay, so it's usually referred to as quantum supremacy. So the title of the paper is Quantum Supremacy Using a Programmable Superconducting Processor. So what did they achieve? So let me very briefly tell you what was achieved here a few years ago. The Google group, they were able to construct a 53 qubit quantum computer. Okay, so 53, it's a quite small number, but for quantum computing, this is not easy. And so they were able to, the amazing thing is that they were able to solve on this 53 qubit quantum device some problem, okay, that is very difficult to solve, and we don't know how to solve it, even with today's largest supercomputers. Okay, so so I should say here, of course, that this problem that they created is a very artificial problem. Okay, so it's a problem that was created so that it is easy to solve on the quantum computer, and it's hard to solve on even a very large classical computer. Okay, so it's only one milestone, but nonetheless it was a very important one to show that at least there is one computational problem that really the only way we have to solve it is using such quantum devices. And otherwise, if we want to solve it, there is no other computational device that we know that can solve this problem. Okay. So, so that's it for the overview I wanted to give. Now let me make a small focus now on a specific topic, very specific topic, which is that I put in my title. It's the task of certified randomness generation. I'll talk in a minute a bit more about this task. So here this part of the presentation will have two parts. So we'll be using a basic ingredient for this protocol of certified randomness generation, which is a very fundamental result in quantum theory. It's known as Bell's theorem. Okay, and I suspect that if you have heard a bit about quantum mechanics, you might have heard of this theorem. It's really a landmark result in quantum theory. And I will tell you how such a result can be exploited in order to generate randomness. Okay, so at a qualitative level. Okay, and then in the second part, this will be the part which will be a bit more technical of my talk. And here I will talk about this tool which we came up with, which we call the entropy accumulation theorem. So this is really, I mean, it's a mathematical tool to precisely quantify the randomness that is generated by a given process. Okay, so and for that, okay, of course, here also I'll stay at the high level, but maybe I'll try to give some details. And okay, given that it's I mean, I cannot in 1 hour to just to give the introduction necessary for the quantum formalism, I will present the classical version of this theorem. Okay, so where instead of having quantum state, we have just probability distributions. We'll be dealing with probability distributions. Okay, so and I should mention that here this is work that we developed over a series of papers in collaboration with several people. So in particular with Frédéric Dupuis from Université de Montréal and the group of Renato Renner at ETH Zurich. Okay, and so yeah, if you would like to hear more, to see more details, so you can check this. The latest paper was recently put on the archive, and it has references to the older versions. But this is, let's say, this is the latest state-of-the-art version. Okay, good. So let me now get into Bell's theorem. Okay, so this I think is actually of independent interest. So I think if you haven't seen this before, then I think it's good to see it once, and it shows you it's in some sense the power of entanglement, of one of the features of quantum mechanics. Okay, so the way one can see Bell's theorem is just as a very simple game. Okay, so it's a game between two parties, which I'll be calling Alice and Bob. Okay, so and these two players, they're not playing against each other. They're cooperating. Okay, so they either win the two together or they lose the two together. Okay, and so how does this game work? So each player, so Alice receives a question, which I call X. Okay, so and this question is just a bit. Okay, so we have question either 0 or 1. And similarly for Bob, he receives a question, which I'll call Y. It's either 0 or 1. And I'll assume that each of these bits is uniform, and they're independent of each other. Okay, so 2 uniform bits. And each one of them, so Alice has to give an output A, depending on X, and Bob has to give an output B, depending on Y. Okay, and the important thing here is that once they receive their questions, they're not allowed to communicate. Okay, so no communication is allowed between Alice and Bob while they're playing the game. Okay, this is crucial. I mean, if you remove this assumption, then it becomes tricky. Okay, and so now I will tell you what the rules of the game are, in the sense that when do I say that they win, and when do I say that they lose? Okay, so the rule is just given by this. Okay, so here, if X and Y is equal to A, X, or B, then I say that they win. Otherwise, I say that they lose. Okay, so this might seem a bit strange, but okay, so let me maybe make it more explicit for you. Is that so? What I want is that if both questions are 1, if X is equal to 1, if X is equal to Y is equal to 1, okay, then I want that the two outputs are different. Okay, so in this case, Alice and Bob win, and in the other cases, if X and Y are so, for example, if X is 0 and Y is 1, then I say that they win if A is equal to B. Okay, and otherwise, I say that the game is lost. Okay, so if this is not satisfied, then the game is lost. Okay, so these are the rules of the game. Maybe it's good I'll leave you a minute or so to digest it and to see, to think about what do you think is the best possible strategy for them to win at this game. And yeah, it's also a good time if people want to ask questions or to propose strategies. Okay, good. So let me maybe propose a very simple strategy. So there is a very simple strategy, which says that Alice always outputs 0, for example, and Bob always outputs 0. Okay, so let's say with this strategy, what is the probability of winning? Let us compute what is the probability of winning. Okay, so remember that X and Y are uniform on 0, 1. So, and here, I mean, Alice and Bob are having a very simple strategy where they don't even look at their input. They don't even look at their question. They just always output 0. Okay, so if X happens to be 0 and Y is 0, then the outputs A and B is 0 satisfies this criterion. It satisfies the winning condition of the game. So in this case, they would win. In the case 0, in the case X is 0 and Y is 1, they also win the game, right? In the case where X is 1 and Y is 0, they also win the game. So in these 3 cases, they win the game because they achieved that A is equal to B. Okay, but of course, when X is equal to 1 and Y is equal to 1, they lose the game, right? Because they're supposed to output A and B, which are different, but they output an A and B, which are equal, and both are equal to 0. Okay, so the strategy that I described, this very simple strategy that I described, actually achieves a probability of winning, which is exactly equal to 3/4. Okay, because we win 75% of the time. Okay, so on 3 out of the 4 possible input pairs. Okay. So this is one strategy. The question is, can one come up with a better strategy that achieves a winning probability which is bigger than 3/4? And so if you think a little bit about it, it takes a few minutes of thought, it's easy to convince yourself that actually there is no strategy, right? So as you have seen with this strategy, if you output, for example, 0 everywhere, then you'll have to be incorrect on one of the inputs. Okay, and so if you do this a bit more generally and assume you have a general function here, you'll easily see that the largest success probability is 3/4. Okay, and so yeah, this is what I wrote here, is that the probability of winning is at most 3/4. And so yeah, in the language of Bell theorem, let's say, this is called the Bell inequality. Okay, so it is a bound on the winning probability that is satisfied by all such strategies. Okay, so as is this game, what is super interesting about it? It's just a random game, and we compute its maximum success probability. What is interesting there? So what is interesting here is that it turns out is when you consider quantum strategies. Okay, so what do I mean by quantum strategies? Again, as I said, I won't get into the formalism of what it is mathematically. If someone has a question, I'll be happy to detail this more. But let's say that the quantum strategy is given by these things. So it's given by an entangled state, so a quantum state, okay, which I denote phi, okay, which is something which is shared between Alice and Bob. Okay, it's something which is shared between Alice and Bob. And the quantum strategy, how will it work, is that depending on the question that Alice gets asked, so which I called X, so Alice will do something that we call a measurement. Okay, so she will perform a measurement on her part of the state. Okay, and this measurement gives an outcome, which I call A, and exactly the same thing on Bob's side. Okay, and so the important thing to note here is that this quantum state is something which they do before the game starts even. Okay, and so this state is something that does not allow you to communicate at all. Okay, so this is something that they can pre-agree on long before the game starts. But really, once the game starts, they do not communicate at all. Okay, they can only use the state which they have prepared before. Okay, and so it turns out that using the laws of quantum mechanics, you can construct such a quantum state phi and measurement devices and description of measurements here, such that this winning probability is some number, so it's cosine squared pi over 8, which is roughly 0.85, and this is strictly bigger than 3/4. Remember, the 3/4 was the bound that we had in the previous slide, right? So we were thinking that we were considering all possible strategies, okay, in the previous slide but it turns out that quantum strategies, they violate this, what I call the spell inequality, right? So these quantum strategies, they go beyond these simple strategies that we discussed last time. Okay, so yeah, so this I mean, now it's really actually in hindsight, it's not a very complicated observation, but it really had very profound consequences of the nature of quantum theory. And this was actually even considering this. So I mean, why did Bell consider this question and come up with such a game? So he wanted to answer a question which was posed by Einstein, Podolsky, and Rosen in this very famous paper in 1935, okay, which they were asking about basically the completeness of quantum mechanics. And so, yeah, there's really tons of work about this in the physics literature. And but for us, we will just try to see how we can actually use this this fact, like the fact that we have a game where the quantum strategies do better than the classical strategies to achieve some task. In particular, here the task of randomness generation. Okay, so now, okay, I would like to use this property. And so,
just a question, please,
sure.
Fawzi.
Yes.
We know explicitly this quantum strategy which gives this probability or not.
Yeah, we know it exactly. Yeah, so I could have presented
Okay.
to you. It's very simple. I mean, you have to give the state, so it's a vector in dimension 4. And these measurements are just a bunch of, I have to give you basically 4 matrices, and here we know it explicitly, fully explicitly.
Okay, thank you.
Okay, so thanks for the question. So now let me tell you how we can use this for randomness generation. Okay, so what I would like to do now is, I call it randomness generation, in the sense that I would like to construct a protocol that at the end of the protocol, it produces randomness, okay, that is certifiably random. Okay, so what I mean by this is that I don't want to trust the person who built this device that outputs the randomness. Okay, so it's in this sense that I call it certified. So and as you know, so randomness is used a lot in for simulation, for cryptography, and so it's important to have devices that allow you to generate randomness, and you would like ideally to have a good confidence that this is true randomness. This is not just randomness that is fake in the sense that it's weak pseudo-random random, or that someone in the context of cryptography, that someone has a copy of it. Okay, but okay, so let me, I won't enter too much in the motivation of considering this task. I just want to generate randomness in a certified way. Okay, and so what I'll do for this is the following. Okay, so I'll describe the protocol in a bit, but in order to get to it, let us consider this scenario. Okay, so let us consider such a scenario which is very similar to what I discussed in the last slide, except that I happen to not know what the devices are doing. So these boxes that I have here, so I don't know what the state is. I don't know what the boxes are doing at all. Okay, so I just know that I have a button that I can press, which corresponds to x equals 0 or x equals 1. And I have also a button y equals 0, y equals 1. And I have corresponding outputs, a equals 0, equal 1, and b equals 0, b equal 1. Okay, and suppose I was able to determine that actually using such unknown boxes, I have that the winning probability is strictly bigger than 3/4. Okay, so then I do know that these boxes, even though I don't know what the boxes are doing, I really know that they cannot be a completely classical strategy in the sense that just I have A is a function of X and B is a function of Y. Okay, because we know from Bell's inequality, if you want, that such strategies are limited by a winning probability of 3/4. They cannot go beyond 3/4. Okay, so there has to be something going on, and so these boxes, again, even though I don't know what they are doing, but there must be something quantum going on. So in the sense that this state has to have some entanglement, and these measurements, they have to be doing something quantum. And more specifically, what I'm interested in is that more specifically, it turns out that the outcomes A and B, they must contain new randomness regardless of how the boxes work. Okay, so just by the fact that these boxes, they win this game with a probability bigger than 3/4, I know that these outputs A and B have to contain randomness. Okay, so they cannot be just deterministic functions of X and Y, for example. Okay, and so yeah, so the fact that it's regardless of how the boxes work, this is really the certified aspect of this randomness generation. Okay, so now using this observation, one can come up with a natural protocol. So I buy this device, okay, this device from someone that prepares such a state and such boxes. I don't know what they're doing, but the person who sells to me this device is telling me that this is supposed to be preparing this entangled state and doing the right measurements, etc. Okay, so and then okay, after getting this device, I use it. Okay, so in the following protocol. So the way I do it is that I will use this device n times in a sequential way. And so each time I give to it as inputs xi and yi. So, okay, so I choose these x and y uniformly at random, and I get the outputs A and B. Okay, so and after using this n times, what I will do is I will count how many times did I win and how many times I lost. So remember, the winning condition looked like this. So it's if x and y is equal to ax or b. Okay, I count the number of times, and this is the fraction. Q is the fraction of such times I won. Okay, and so two things. Either this fraction happens to be smaller than 3/4. Okay, in this case, then I say this device is not good. Okay, so the person who sold me this device is not working very well, so I just abort the protocol. Okay. But otherwise, and this is what we are supposed to have, right? If the device is working properly, then okay, I will look at my outputs, so A1, B1, AN, BN. Okay, and from this very qualitative argument that I made before, we know that there should be randomness in these outputs. Okay, so what I will do is then I will apply some deterministic function, which I call G here, to these outputs, and this will give me Z1 to ZL. Okay, and the objective is that I would like this Z1 to ZL to be uniform random bits. Okay, so yeah, okay, I didn't say that maybe, but so of course the objective in randomness generation is to generate uniform random bits. Okay, because then I want to use them for example, in a cryptographic application or something else. Okay, and this is just the Z1 to ZL would be the outputs of my protocol. Okay, so this is the rough idea of how the protocol would look like. And so the whole thing I want to motivate now is I want to be able to quantify precisely how do I quantify the amount of randomness that is present in a given random variable. So here, this A1, B1 to AN, BN, this is a random variable. I'm saying here it contains some randomness, but I didn't say quantitatively how much randomness there is and what is the right way of quantifying the amount of randomness in this bit string. Okay, and this is what I will get into next, is how to quantify randomness. So let me check on time. Okay. Okay, good. Okay, so probably the measure of randomness that maybe many of you are familiar with is the Shannon entropy. Okay, so for a given random variable, let's call it A, I consider everything as discrete here, right? So this has probability distribution P, okay, which I denote P, and PA. And so the Shannon entropy is just given by minus the sum over A of the probability of A times log of the probability of A. Okay, so this is a widely used measure of randomness. And so you see here, it has the natural properties you would want. So if A is deterministic, if it always takes a specific value A0, then the Shannon entropy is 0. Otherwise, if on the other extreme, if I have something which is uniform on a set S, then the Shannon entropy gives you log S. Okay, so this is it is indeed like measuring in some sense the amount of randomness in a given random variable, but so does it really capture the property we want to capture, which is the amount of extractable randomness, right? So remember last time, or not last, I mean the last slide. Sorry. In the last slide. Here, what I want to really, the thing I want to quantify is this L, right? How many bits of randomness are contained in A1, B1 up to AN, BN. Okay, so for that, to understand this, let us look at one specific distribution, which will play an important role here, and which will tell us, which will tell us that this Shannon entropy is really not the right measure for that. Okay, so let's consider this distribution on bit strings of length n. Okay, so I have a bit string. So A is a bit string. So A1 to AN. A1 is the first bit, AN the last bit. So, and suppose it has the following distribution. Okay, so it's generated in this way. So suppose that A1 is uniform, random. So A1 is a uniform bit. But depending on A1, so if A1 is 0, then all the next ones are 0 as well. Okay. And otherwise, if this A1 is equal to 1, then the remaining ones are all uniform, completely uniform and random. Okay, so this is a well-defined distribution. So I mean, the reason I call it L here is just because if you write its histogram, right, it will look like an L, right? Because basically the probability of the all 0 string is a half, right? So because it's so the first one has to be 0, and then this is always 0. So the probability of all 0 is a half. So that's why I have a big probability half, but all the other elements are equal, have the same probability, which is roughly a half times 1 over 2 to the n. Okay, so if you try to compute the Shannon entropy of this bit string of length n, it's easy to see that it's roughly, okay, it's not exactly this, but up to a very small constant. It's n plus 1 over 2. Okay, so roughly n over 2. Okay, so it's roughly n over 2. Okay, so here you would expect that there is still, I mean, there is basically n over 2 bits of randomness in such a source A. However, if you think about it in terms of extractable randomness, so remember what I mean by extractable randomness is that I have to be able to apply function G on my bit string A, okay, in such a way that so G of A should be uniformly random, okay. But here I have uniformly random on bit strings of length L. Right? So if I take something which is uniformly random on bit strings of length L, then every element there has a probability of 2 to the L, probability of 1 over 2 to the L, right? But I have here a specific element, which is G of 0, which has already a probability of 1/2, right? Because A is equal to 0 with probability 1/2, right? So the probability that G of A is equal to G of 0 is at least 1/2. Okay. And so by this simple argument, you see that actually for this distribution, L cannot be bigger than 1, right? Because I have a specific element which has probability 1/2, and it's supposed to have probability 1/2 to the L, right? So L cannot be bigger than 1. Okay, so for this specific source, really there is almost no, I mean, there's only one bit, at most one bit of randomness I could extract. Okay, whereas the Shannon entropy, it told me that there was n/2. Okay, so okay, so this was a simple argument. I mean, it's relatively simple to generalize this slightly and to see that actually the relevant measure is not the Shannon entropy, but more of a worst case kind of entropy, which I call the mean entropy. So the mean entropy of a given random variable A is just, it's very simple. It's just minus log of the maximum value of the probability. Okay, so instead of here taking these averages, here it's just the maximum. Okay, the maximum probability, and I take minus log. And yeah, so in general, the mean entropy and the Shannon entropy can be quite different, in particular for this L distribution, where we see that the value of H min is 1, whereas the value of the Shannon entropy is n/2. Okay, so in general, H min of A is smaller. That's why it's called H min, because it's in some sense the smallest. But in general, it can be much smaller than the Shannon entropy. Okay, and yeah, so I won't get into the details of the other side of how you can actually extract this many bits, but it turns out, okay, so it turns out that really this mean entropy, so the mean entropy of A, it really characterizes the number of bits of randomness you can extract. So if the mean entropy is small, then you cannot extract many bits. But if the mean entropy is large, then you can extract this many bits of randomness. Okay, and so a small technicality here is that we usually, I mean, it's usually quite important to smooth this quantity, in the sense that you allow for small failure probability. Okay, so here just, yeah, it might be useful to illustrate this mean entropy. So here I put this histogram. This is an example of a probability distribution, and you see here that if I look at the maximum, and minus log of that is the mean entropy, and the smooth version, if you want, is that you're allowed to remove some of the probability mass, provided that you don't remove more than a total mass of epsilon. Okay, good. So okay, so this is so yeah, the important message here is that what characterizes the number of bits of extractable randomness is this entropy measure, so the smooth mean entropy. Okay, and so now my objective is, for this specific protocol that I mentioned, but more generally even for other setups, my objective is to evaluate this mean entropy of A1 to AN for this, for example, for my specific protocol that I described a few slides ago. Okay. So the thing is that in general, computing such a smooth entropy is a hard task, and yeah, here's where entropy accumulation will come in. This result I was mentioning, and so this entropy accumulation will allow us to compute this smooth mean entropy of a large system by decomposing it in two parts. Okay, and so yeah, so ideally I would like to say, okay, so the entropy of this big system A1 to AN is actually the entropy of the first system plus the entropy of the second system plus third system, etc. Okay, so yeah, so this would be the ideal thing I would like to do, but this at least the naive way of doing this, it doesn't hold at all. Okay, so yeah, for example, for this L distribution I talked about, so the mean entropy of the whole A1 to AN is equal to 1, but if you take the marginals AI, okay, so if you just take the marginals here, you'll find that each one of them has a non-zero mean entropy. So if you sum over the different i's, this will give you something which is linear in n, okay? And of course, this is very different from the true value of 1. Okay, so, but this is what I would call, this is naive additivity. Okay. Yeah, so a quick remark is that there is some form of additivity that holds for the von Neumann entropy. It's sometimes known as the chain rule. Okay, but yeah, so such a thing does not really hold for the mean entropy. Okay, so but let us get back to yeah, so computing this smooth mean entropy, and I would like to decompose it into parts. Okay, so as I said before, naive additivity does not hold, but the main message for entropy accumulation is that if you compute the parts, if you compute the contribution of each part in the right way, then such an additivity does hold. Okay, so in the sense that you can lower bound the smooth mean entropy by a sum of the contribution of the ith part. Okay, so it will not be as simple as just the mean entropy of the marginal, but it will, and I will show you what it is. Okay, and so, okay, in order to make such a statement, then I need to define a model of how do I generate the systems A1 to AN. Okay, so yeah, I'm probably taking a bit too much time, so I will so yeah, maybe Rafiq, how much time should I try to finish in 5 minutes, let's say, or?
Yes, 5 minutes, 7 minutes.
5 minutes is good. Okay, so yes. I'll try to finish in 5 minutes. So I'll skip lots of things, but but maybe I'll try to make clear the main message. So okay, so as I said, so I will define a general model for generating these systems A1 to AN. Okay, and my functions now, the contributions of the parts will depend on this specific model. Okay, and so the way I will do this is that I will assume that my process is generated in this way. So I have these maps. Okay, so in the quantum case, these will be quantum channels. If some of you know about quantum theory, but in the classical case, these are, think of them as just stochastic maps. Okay, so which take as input a random variable and output these two random variables S1 and A1, etc. Okay, so you can see them as stochastic matrices if you want. Okay, so yeah, these are maps and they generate my random variables A1, A2, A3 up to AN. Okay, notice that for any joint probability distribution on A1 to AN, I can construct such maps, right? So so in particular, I can just generate A1 and then I put in S1 a copy of A1, and I say that A2 is this stochastic map. What it would be doing is it's generating A2 conditioned on A1. And same thing. And S2, I would put A1 and A2, and then A3 would be this map. What it would be doing is it's generating A3 conditioned on A1, A2, etc. Okay, so yeah, so just to say that in general, I can put any probability distribution in such a framework. But what will be the case is that for the settings of interest, like, for example, the protocol I was mentioning, for analyzing the protocol I was mentioning, these maps will come in naturally, actually, from the analysis of our protocol. Okay, so just to get familiar with this model, let us see the two simple examples and how to put them in this model. Okay, so remember our L distribution, which we saw several times now. So the way we could generate this using these maps is that, okay, so the first map, what it's doing is it's just generating a random bit, okay? And it is outputting this random bit. So A1 is equal to this random bit R, and it's putting in this, you can think of it as a memory state if you want. So the state of S1 will be R, okay? So that I keep this R in memory. Okay, and so the other maps, what they will be doing is they will just be keeping the memory state. So Si is equal to Si minus 1. And if Si minus 1 is 0, so if the state is 0, then my output is deterministic, it's equal to 0. Otherwise, my output is uniformly random. Okay, so it's very easy to see that this exactly generates this L distribution. And okay, so this was the first example. The second example is when A1 to AN are IID. Okay, so they're independent and identically distributed. And in this case, then I don't need any memory at all, right? So I can let these maps generate fresh copies of A, right? So M1 just generates A1, M2, there's no memory at all, generates A2, etc. Okay, and so now I'm in a position to tell you what will be the contribution of the ith part to the global entropy. Okay, so remember here, I said f of AI is the contribution of I to the global entropy. And so now I can tell you as a function of these maps now, what is the contribution to the global entropy. And so the contribution will be given by this formula. So we'll take the Shannon entropy, okay, of the output of this map, okay, of this ith map, but not on an arbitrary, I mean, I'll take it on the worst case S. So I'll take the S that outputs the smallest Shannon entropy. Okay. And this will be my contribution. Okay, so let's check that for these two setups. Okay, let's compute this at least for these two setups. So for the L distribution, if I try to compute this f of M1, okay, so the output of M, it has no input, right? So the output is always uniformly random. So there is one bit of randomness. Okay, but for the further ones, for Mi with I bigger than 2, the f of Mi is equal to 0, right? Why is that? Because if small s is equal to 0, then the Shannon entropy is equal to 0, right? So there's no randomness at all. Okay, and in the second case, where I have no memory at all, then this minimization disappears, and so I just have the Shannon entropy H of A. Okay, and so this is where, so the first version of the entropy accumulation theorem tells you exactly that, which I said before, is just that the smooth mean entropy of a joint system A1 to AN is lower bounded by the sum of these contributions, where the contributions are measured in this way by taking the worst case Shannon entropy. Okay, so there's some square root 10 corrections. And so yeah, this works well on these two examples. So on the L distribution, it gives you nothing non-trivial, which is expected. And in the IID case, this gives us the well-known asymptotic equipartition theorem. Also, this is a consequence of the law of large numbers, if you want. And so so we get this result. Okay, so given that I went a bit slow, then okay, I will skip how you use this for our randomness generation protocol. Okay, this is a further version which takes into account the statistics, and maybe I will just conclude. And if you have further questions, I will take them. So so yeah, let me just summarize and conclude. So what I presented is, I presented a game, right? This simple game that I presented, for which quantum strategies are strictly stronger than classical ones, where with quantum strategies you can do something that you could not do classically. And I showed you how you can exploit this to certify randomness generation. And I also tried to discuss how to quantify the amount of randomness that's produced in such a protocol. And showed it was this function f. Okay, and I will stop here. Thank you.
Thank you for Omar. Thank you for this nice talk. Are there any questions, please? Any questions? I have a question, maybe a naive question. Is this related to digital trees, the quantum theory? It is related to digital trees.
So I'm not sure I know what digital trees are.
Digital trees is a binary tree constructed by code 0 or 1. 0 we go to the left, 1 you go to the right. By digits.
Ah, okay.
0 and 1.
So it's binary trees that are labeled by the digits.
Yes.
Let me see if I see a connection. I don't see any connection, sorry.
Okay, perhaps maybe. Okay, if we can go to slide 11, please.
Yes.
So what do you mean by the conditional H, A, K given A1, A2, A3,
yes.
AK?
Okay, so yeah, I didn't define the conditional entropies. So for the Shannon entropy, the way the conditioning is defined is you can think of it as the expectation over the, so okay, for concreteness, let's consider this term, like the term H2 condition on H1, H of A2 condition on H1. So this is the expectation over the values of A1 of the Shannon entropy of the conditional distribution, right? So for every value of A1, so let's call it little a1, you have a conditional distribution. So P of A2 conditioned on A1 equals little a1. So this is a valid distribution. I can compute its Shannon entropy. It's just the expectation of this Shannon entropy. Yeah.
Okay, that means the conditional expectation of Shannon entropy given A1.
Yes, exactly. Yes.
And the last A and minus 1, you mean? Huh?
Yes. Sorry. Yeah, indeed. Yeah, thanks. Yeah, this should be an element.
Okay. And in slides between 5, 4, 3, I think, when you get 53, the problem with 53, 5, maybe 4 or 5. Huh?
Yeah, 53 qubits. Yes, this.
Yes. Why exactly 53? Why
this is what they were able to construct, right? So actually, so this is their quantum hardware has actually it was aimed to be 54 even, but one of them was dysfunctioning, right? So because they put their qubits on a square grid.
Okay.
So they were able to construct 54 qubits, and one of them was not working, and so they just didn't use it, and so they used 53 qubits. I mean, this is just because this is what they were able to construct. I mean, now they have bigger quantum computer. I mean, they have bigger devices with roughly 100 qubits, but at the time, this is what they had, and this is, I mean, they had 53 relatively good qubits.
Okay. It is the first talk in our webinar about the quantum theory. Can you give us, in 2 words, what is the main difference between quantum computer and the classical computer? Just
so you mean on a mathematical level, or on a, I mean, I try to give you here the things, the potential things you can do on a quantum computer that is that is better. But maybe what you want to is more of a mathematical description of what the difference. Yes. So um, uh, okay, let me maybe try to explain this way, is that okay, so as I said, a qubit, right? The state of a qubit is a vector in dimension 2, okay? And so maybe the key thing about a quantum computer is that, so now if you have a quantum computer on n qubits, right? So then this is the way to represent such a state is a vector in dimension 2 to the n, right? So, or in other words, it's you can see a quantum state on, let's say, 53 qubits, just for concreteness, on 53 qubits as a superposition of arbitrary bit strings of length 53. Okay, so it's a vector really in a vector space of dimension 2 to the 53. Okay, and so the reason, the computational power of quantum computers comes from the fact that it's, as you're doing your computations, the state of your memory can be in a very complicated state. In this very high dimensional, it's a vector in this very high dimensional space. And this is the reason actually we cannot simulate it classically, because if you try to simulate it classically, you would need to keep this vector in this very long dimension. And that's why it's roughly at when you start reaching 40 and 50 qubits that we start seeing this quantum supremacy. Because if you're below 40, like let's say 30, like 2 to 30 is not that big that you can simulate it on a classical computer. But now 40, 50, this is where you start seeing phenomena.
Okay, thank you. Thank you.
Can I?
Yes, Nabil, yes.
Just a precision about using quantum theory for numerical analysis, for example, for solving linear systems. Then, if I understand, it's not the fact to have new algorithm, but just to write the same algorithm by another way. But is it true?
Yeah. So okay. So for okay, so yeah, in this in this third bullet that I have, there's several kinds of algorithms, and so some of them it's solving exactly the same problem. Like, so for example, you could be trying to solve so imagine, you have a linear system, you have an A and a B, and you want to find the X and X such that AX equals to B. Okay, so this is a well-defined problem. And so A and B are given in the usual sense, like it's, or they're completely described. So you describe them coefficient by coefficient. Mm-hmm. So for this problem, so for this computational problem, and the objective is to find X. For this computation problem, as far as I'm aware, we don't have any speedups with quantum computers, right? However, the problem for which we have a quantum speedup is basically where, let's say, so A and B are given in in a concise quantum form, okay? And for such in such a setting, we do have an exponential speedup. So I mean, it's not the kind of standard problem of solving a linear system. So for example, this famous paper of HHL, it's not solving exactly the usual linear system solving problem. It's solving a slightly different problem where the inputs and the outputs are given in a concise form. Okay. And in this case, it's able to have an exponential speedup. But okay, so this is the
okay, but yes, then if the matrix and the right hand side
yes.
are given in this quantum sense, we have a speed up. But if it's not, can we write an algorithm in the quantum size without having a speed up, or we cannot?
No. So okay. So a classical computer is a special. I mean, so with a quantum computer, you can in particular do every classical computation.
Okay.
So yeah. If I mean, so yeah.
Okay,
Maybe this I didn't say, but so if you stay, for example, if you don't use this ability to do superpositions, you just stay in what we call sometimes the computational basis.
You have only one state. Okay. Yes, that's that.
So it stays classical, and every classical algorithm you can
Okay.
run it.
Thank you very much.
Other questions? So thank you, merci, شكرا again فوزي عمر for this nice talk. وخليني نقول لك بالعربي لانه كنا عرب لهنا انه احنا فخورين بيك فوزي عمر وبارك الله فيك.
بارك الله
كثيرا.
شكرا.
رمضان كريم. شكرا فوزي.
رمضان كريم. السلام عليكم. السلام عليكم.
السلام ورحمه الله. الى اللقاء.
شاي طيبة.
شاي طيبة نبيل. اللقاء بالسلامة. شكرا. لا حضور مشرف اليوم.
لا.
شكرا يا حاتم. ان شاء الله تبقى معنا اخويا.
ان شاء الله. شكرا. سلام.
اهلا. انا حاتم.
ربي معك. عايش.
الى اللقاء.
الى اللقاء. بعد العيد نبيل.
ان شاء الله. ان شاء الله.
ان شاء الله. السلام عليكم.